In this class, we will solve a linear programming problem using graphical method. This is the given problem. A firm produces two types of paints. The specific amount of material, labor and machinery hours required to produce each paint and the availability of each of the resources are given below in the table. If the profit for each thing of paint A is rupees 2000 and for paint B is rupees 1500, we have to formulate a linear programming problem and also we have to obtain the optimum production schedule. That means, this is a problem of maximization of the profit. So here, because in optimization, if you take up cost of a project, then we have to minimize the cost. If you take the profit there, then we have to maximize the profit. So these are the data given. There are two types of paints here, paint A and paint B. So the numbers given in this table are the number of tins and the required labor. Actually, for the availability of labor is only 12 hours, availability of machinery is only for 6.9 hours, and availability of materials is only 4.9 kgs. So units are different here. Now we have to find out how many things of paint A type and how many things of paint B type we have to manufacture so that the profit is maximum. So I will take let X be the number of tins of paint A that has to be produced for maximum profit. Y be the number of tins of paint B. So these two are unknowns. So we have to maximize the profit here. Let me take Z as the profit. So we have to maximize this profit. So maximize. Now let us formulate the problem now. Maximize Z is equal to, see, X is the number of tins of paint A. If you take paint A, the profit obtained for each tin is rupees 2000. Therefore, we have to maximize 2000 into X. So where X is the number of tins that should be produced. Plus, if you take the profit of paint B per tin as it is 1500 and number of tins we have to produce is Y. So this is the function. This is the function. So Z is a function of both X and Y. So for one tin of paint A, 2000 rupees is the profit. For one tin of paint B, 1500 is the profit. So we have to, once you find X and Y, then you can find out the maximum value of that Z, that is the profit. Now, you know that optimization problem will involve constraints also. So this table gives the constraints. Now we have to develop the constraints. We have to maximize this subjected to. Now let us write the constraints now. Now here, taking X and Y as the number of tins of paint A and number of tins of paint B for maximum profit. So here, what we can write here is the first constraint will be with respect to the labor. With respect to labor, we can develop the constraint like this. So 3 into X plus 2 into Y, and since availability is only 12 hours, this should be less than or equal to 12. Please note that this is less than or equal to problem because maximum availability of the resource is only 12 hours. So this is what is the first equation. Next, for the second equation, for the machinery, the constraint will be 1 into x plus 2.3 into y should be less than or equal to 6.9. So in maximization problem, this is the maximum value. So whatever value you have to get, it should be less than or equal to this. And the third constraint is for the materials. So there are three constraints here. For the material, the equation is 1 into x plus 1.4 into y should be less than or equal to 4.9. So these are the three constraints we can have for each of the inputs. Now of course in a linear programming problem, so we can see that x and y, they are positive. That means the actually the condition to be written is x greater than or equal to 0, y greater than or equal to 0. That means these two values are non-negative. So that means you can have either 0 or positive value. Understood? Number of things cannot be negative. It can be 0 or it should be positive. So now this is the problem. So this is the problem, a linear programming problem, which we can now analyze or solve using graphical method. So in the last two videos, I have explained the method of linear programming by graphical method. Now we have to proceed the same procedure here. So here we have developed the equations now, or we can say that we have formulated. So we have formulated the optimization problem now. Now we have to find out the x and y so that z is maximum by graphical method. So the method is like this. So first these three inequalities we have to convert to equality. So we have to convert them to equality. Equalities will be now, the first one will be 3x plus 2y is equal to 12. The second one is x plus 2.3y is equal to 6.9. Third one is x plus 1.4y is equal to 4.9. So these are the three equalities. Now we have to plot these three straight lines in a graph sheet. So let us take like this. X-axis I will take. Only in first quadrant you have the graph, because as I already told, both x and y are positive here. So you won't get any other quadrant. Only first quadrant you are going to get. Now let us have the scale like this. So here, to plot the points, first I will take this 3x plus 2y is equal to 12. So put x is equal to 0. Same procedure we are following. Find out y. So y will be 2y will be 12. Therefore y will be 6. If you put y is equal to 0, x will be 3x will be 12. Therefore x will be 4. So what you can say now? So on this, if you want to plot this 3x plus 2y is equal to 12 straight line, so I have to take these 2 points, 0, 6. X is 0, y is 6. So 0, 6 is, so this is 6. And another is x is 4, y is 0. So somewhere here. So this is 4, 0. This is 0, 6. If we join these 2 points by a straight line, so this is the first line, first equation. So this is the first equation. So the first equation is this: 3x plus 2y is equal to 12 is this straight line. And second equation, x plus 2.3y. X plus 2.3y is equal to 6.9. Similarly, if you take x is equal to 0, y becomes 6.9 divided by 2.3. It is 3. Okay, it is 3. Y is equal to 3 you get. Then y is equal to 0 is equal to x, you are going to get 6.9. So these two are the points for drawing the second straight line. So now if I plot those points, x is 0, y is 3. So y is 3 means somewhere here. So this is 0, 3. The other point is 6.9, 0. 6.9 will come here. 6.9, 0. You can plot this on a graph sheet. Okay. Now this is the second. If you join these 2 points by a straight line, this is the second equation. So this is second equation, that is the graph. Then similarly, if you take the third one, third equation is x plus 1.4y. X plus 1.4y is equal to 4.9. So therefore, if you take x is equal to 0, y becomes 4.9 divided by 1.4. So using calculator, let us find it. 4.9 divided by 1.4 is 3.5. 3.5. Then if you take y is equal to 0, x will be of course 4.5. So to plot this third equation, so the points are 0, 3.5. So 3.5 will come somewhere here. So somewhere here, 0, 3.5. So the other point is 4.9, 0. So 4.9 will come somewhere here. So this is the point 4.9, 0. So if you join these 2 points, so something like this you are going to do. Okay? So this is equation 3. So this line represents equation 3. So all the 3 constraints now we have plotted on a graph sheet. You can use a better scale to have it. Next, what we have to do now is we have to take the common region, or we can call it as feasible region. Feasible region in this graph, so that it satisfies all the 3 constraints. So all the 3 constraints are less than or equal to, therefore feasible region naturally lies below this. So this becomes the feasible region. So because it is less than, so it is below the line. If it is greater than, then it comes above the line. So all this I have explained in the earlier 2 lectures. Now we have to find the values of x and y at the boundaries of this feasible region. Now this becomes the feasible region. So if you see here, so this is the feasible region. So the boundaries I will take it as, of course, origin is one boundary point. Corner points we have to take. I will take this point as A. This is one point. Then B will come somewhere here. So this you can exactly get when you plot the graph, and see somewhere here. One more point you are going to get somewhere here. C also will be there. And D will be this. C you are going to get somewhere here, where these 2 lines cut. So actually this becomes so one more point C you are going to get somewhere here. You can just after plotting you can get it. One more point C you get. So totally you will be getting A, B, C, D. 4 points you are going to get. So the graph will be something like this. If you plot on a broader scale, so you will get the feasible region like this. So just I am going to show one more point will be there here, and another point will be there here, and one more point will be here. So this is how you are going to get A, B, C, D. This becomes the feasible region. There will be 4 points, of course. There will be 4 points. So the points joining 0, 6 and 4, 0, 6 and 4, 0 is one line. 0, 3, 6.90 is another line. 0, 3.5 and 4.9, 0 is another line. So if you take the corner points, so these are the corner points. A, B, C, D are the corner points. Of the feasible region. So we have to get the coordinates of those points. So if you get the coordinates of those points, the final and we have to find out the values of z at all the 4 points. So next step is find the coordinates A, B, C, D. Of course, out of these four, A is known. 0, 3 is A, and 4, 0 is D. So we need to find the coordinates of B and C. So A is, as we know, it is 0, 3. That means X is 0, Y is 3. D, we know that it is 4, 0. That is X is 4, Y is 0. B, if you plot the graph, roughly you are going to get B as X is 1.75 and Y becomes 2.25, something like this. Okay, can just check it. Then C is X is 3.2 and Y is 1.25. So these are the points, X and Y points, X, Y values, coordinates of these 4 points. Now we have to find out the value of Z at all these 4 points. So Z is given by 2000 X plus 1500 Y. Now let us find out that Z value at all the 4 points A, B, C, D, and whichever is the maximum value of Z, that gives the answer. So that is maximum profit. So let us find out the value of Z at all these 4 points now, just by putting the values of X and Y. So let us see now values of Z at all the boundary points. So at point A, Z is equal to 2000X, that is 2000 into X is 0 plus 1500Y. Y is 3. So you are going to get 4500. Of course, it is in rupees. Then at point B, Z is 2000 into 1.75, X is 1.75 plus Y is 1500 into 2.25. This is the value of Z. If you simplify this, so 1.75 into 2000 plus 1500 into 2.25. 1500 into 2.25. So it becomes 6875. 6875. Next at C, Z is equal to 2000 into X value is 3.2 plus 1500 into Y value is 1.25. So if you simplify this, you are going to get 2000 into 3.2 plus 1500 into 1.25. 1500 into 1.25. 8275. And lastly, we have at D, Z is equal to 2000 into X value is 4 plus 1500 into Y value is 0, which comes out to be 8000. So among these four, the highest value, maximum value is that 8275. That is at point C. So at point C you have the highest value. So maximum value is this. We have to get the maximum value, maximum Z there. So maximum profit is equal to rupees 8275. So the number of tins paid A, number of tins of paid A is X value. X value is you are going to get 3.2 there. So 3.2 tins. And the number of tins of paint B to have maximum profit is Y value, which is 1.25 tins. So this is the final solution. So these are the number of tins that will be manufactured to have maximum benefit or profit of 8275. So in this problem we have formulated the linear programming model, and then we have solved the model by using graphical method. So we had to plot the graph using a correct scale. So maybe 1 centimeter is equal to that 1 unit, you can take it as 1. So then you get 6.9 centimeters here, 6 centimeters here on this. So neatly you can draw the sketch. Then you have to plot the feasible region. Feasible region is a region which satisfies all the constraints. So since here all the constraints are less than or equal to, feasible region will be below all these lines. It is a common region which satisfies all three constraints.